Hey everyone, this is Dr. Walker. Let's finish the example number 2 from video 576. We just did part A in the previous video where we found the magnetic field at a point a distance x away from a loop. Now we'd like to find the field at the center of the loop. So we know that we can use the Biot-Savart law for this, and it's written down right here. I have drawn the loop here in the YZ plane, since we don't need to be out away from the loop anymore. The first step is to draw the ds, and I was starting to draw it here. I just pick a random location for ds, and then the next thing is to draw the r hat. And remember, ds is a length element that points in the direction of the current. The current is going counterclockwise. Then r hat points from ds to the point where we're trying to find a field. And we write down this cross product, and we can go ahead and figure out which way dB is going to go by pointing our fingers to the left and folding them down in the direction of r hat. We'll see that the dB is out of the page. If we repeat this for another random segment, we'll see that the field is still out of the page. So this makes it easier than the last part, because the field is always pointing in the same direction, so we will be able to integrate. Before we integrate, let's go ahead and simplify the cross product. We have mu naught over 4 pi I. Notice the angle between ds and r is always going to be 90 degrees, since ds is tangent to the circle and r is along the radial direction. So when they're perpendicular, the cross product simplifies to ds times 1 sine of 90, which is just ds. And for the radius here, and since in the previous problem I went ahead and changed the radius to capital R, let's just use capital R right away. R squared for the radius. And then the direction we said is out of the page, which is going to be the x direction is out of the page. So that would be the I hat here. And now we're ready to integrate our magnetic field. And I'm just going to find a magnitude right now so I don't have to keep putting the direction in. Is going to be the integral of dB. So the integral of this part, which is mu naught 4 pi I, r squared is a constant. So we're just integrating over ds. We can, once again, write ds as rd theta. We can define a theta here. Last time we called it phi. We can still call it phi if we want to. So rd phi. And just to do it a little bit differently, you don't have to change it to rd phi. When you're just integrating ds, that just means that you're integrating along the length, and the length is just going to be the circumference of the circle. So we can just go ahead and reduce the integral of ds to the circumference, which is 2 pi r. Or you can go ahead and write it like this and integrate from 0 to 2 pi. You'll get the exact same thing. So whichever way that you prefer to do it. You're going to get mu naught over 4 pi I r squared, and then we're going to get 2 pi r for that integral, and then we can go ahead and simplify. We're going to cancel out the pi, cancel out the 2, cancel out one of the r's, and we are going to get mu naught I over 2r. So that is the field, and it is along the x direction for this particular loop. So this is the magnitude of the field. Now, since we did part A, and when we did part A, the result that we found, I wrote it down here. We could also use this result to obtain our new result for the field at the center of the loop. For the center of the loop, it just means that our distance x is equal to 0. Because we're not at any distance from the YZ plane. We're in the YZ plane. So we can just rewrite this with our x equal to 0, and you can see what happens. right? Let x equal to 0 in this expression, and then that's going to cancel out the x squared here, and then we're going to have mu naught I r squared over 2, and then r squared to the 3/2 is r cubed. So then one of the r's will cancel out, the r squared will cancel out, leaving us with 1r here. So we do get the exact same thing that we got using the Biot-Savart law right here, get the exact same answer. And since I have vector form here, I'll go ahead and put vector notation for this one. Let's look at the last part where we're trying to find the field at a point very far away from the loop. I have our expression that we found back in part A again. If we want the field at a distance very far from the loop, then that's going to be the approximation that x is going to be much, much greater than the radius, which is r. X is going to be much, much greater than r. So what happens in this case is that we can neglect the r squared term here since x is much, much greater than r. And that's going to give us mu naught I r squared over 2, and then x squared to 3/2 is x cubed. And if we want vector form, in this case it will be I hat. One last thing to mention here is that you can rewrite both part B and part C in terms of the magnetic moment. If you write this one here in terms of the magnetic moment, you're going to get mu naught. Oops, I forgot to, sorry. Oh yeah, no, that's fine. Let's see. Let me try that again. If you rewrite it in terms of the magnetic moment, you're going to get mu naught mu over 2 pi x cubed in the I direction. And if you rewrite the other one in terms of mu, this one right here, you're going to get mu naught mu, and mu is a vector, so we can put that vector notation, over 2 pi r cubed. So what I would like you to do, if you would like 5 points extra credit on test number 3, since you made it this far in the video, is I just want you to show how to get from here to here, right? And it's just a matter of remembering how mu is defined to get from one to the other. Show how to get from here to here. And again, it's just going to be 1 or 2 steps. It's going to be very quick. And so do that, and then also go back to our notes from chapter 5 when we found the electric field due to a dipole. There was an example that we did where we found an electric field due to 2 charges, and then we looked at a special case where it was a dipole. And just write down the expression that we got for the electric field due to the dipole, and write it in terms of the dipole moment P, which was defined in that chapter as well. If you just look at our notes, it should only take you a few minutes, and you write down the expression for E in terms of P, and then you'll see how close it is to, and this is supposed to be a cubed, not a squared. Good thing I cut that. You'll see how the electric field due to dipole looks very similar, like the electric field due to a current loop when you're very far away from that loop. And then just email me your answer. Thanks everyone. I hope you enjoyed the video.